Okay, so let me also start out by thanking the organizers for putting together this wonderful workshop, which is very nicely timed. So what I'm going to talk about is some work in collaboration with Renata Carlos and some students of mine in the postdoc. And like many other talks, it's related to this recent conjecture, Swampland de Sitter conjecture from Qumrun and collaborators that kept many of us very busy this summer. So essentially, as we have heard before, it calls kind of for a paradigm change. So in the second paper, they mentioned inflation could be alternatively replaced with some kind of string gas cosmology, bouncing cosmology, or who knows what. If this C is close to order 1, I mean, current bounds, I think, as we heard, is 0.1 or 0.09. And similarly, it kind of forbids the Sitter vacua and calls for the replacement in terms of quintessence, a rolling scalar field. Okay, now my kind of one-slide introduction is, essentially current experiments test this kind of bounds. So large field models of inflation are currently being tested. So this is closely related to the weak gravity conjecture, as we have heard in many talks. Similarly, this de Sitter Swampland conjecture calls for quintessence with C of order 1 is also being currently tested by many experiments. And the C order 1, I think, is already at the boundary of what is possible with current observations. So Qumrun and company, they give 0.06 as, I think, 2 sigma bound. So both of these experiments, they are kind of at the bound. 0.6, sorry, did I say 06? Okay, no, so it's 0.6, not 0.06. 0.6 and 0.09 for inflation, I think. So in that sense, if we for some reason live at these boundaries, it's very interesting to get concrete string models to study that further, to understand that very well. I think we all agree on that we as string theorists should make a lot of progress. And maybe I'm young, maybe I'm naive, but maybe there's a hope that we can actually do that in the same time frame like these experiments. Thomas von Ried said 10 to 20 years. Fernando said probably not before we die or something. So I have the hope maybe we can make some progress even within the next 10 years, and maybe we can say something very concrete before the experiments tell us this is the answer, and then we try to reproduce it from string theory. Here we have a kind of opportunity to make predictions for the experiments. So what I'm going to talk about is more concretely about this conjecture. What Qumrun said, it's with all these conjectures, it's generically very hard, impossible to prove them, because we don't really understand non-perturbative string theory. Somebody asked, do we really understand whether there are more theories of quantum gravity? So if you want to say something about all theories of quantum gravity, it's somewhat difficult to prove them, but one can gain support for these conjectures by trying to disprove them. So Thomas was a little bit apologetic. I wouldn't be too apologetic. We tried to somehow construct something and see whether it's consistent with the conjecture or whether it's in contradiction with the conjecture. And then accordingly, we adjust the conjecture. I think this is how science works. And for this de Sitter Swampland conjecture, there seems 2 clear paths, which people already mentioned before. One is we can try to scrutinize KKLT and spell out explicitly the shortcomings in KKLT or in LVS. This is one of the things that has been going on as a debate for many years, unfortunately, and we still haven't been able to settle this. So it would be great if out of this conjecture now maybe we see some progress here, where people can agree at this point there is an issue, or no, there is no issue, everything is fine. Is unclear. But there's also to study these kind of phenomenologically viable, interesting models that exist in string theory. One can also try to come up with new, maybe simpler constructions that might not necessarily be fully phenomenologically interesting, that are first some kind of toy models that might or might not be made consistent with. So we can try to construct very simple de Sitter vacua in string theory, and we can see whether they are consistent with the conjecture or to consistent. So in that sense, we would gain support or disprove. And kind of what I wanted to talk about in this talk about a particular class of, in some sense, simple or constructions in string theory that have been studied and that I'm revising, and hopefully other people. So what I want to talk about string theory, and as a quick recap, I discussed type 2A on Calabi-Yau threefolds. So this was studied, Villadona, I cite this, Lewis and Grimm, other people. Essentially, it has some advantage to type 2B, where you only have F3 flux, that you have F0, F2, F4, you have even, and if you include hat pole, and it allows you surprisingly to stabilize all moduli basically already. So if you're in large volume V coupling, which you can be in ADS, then you have all moduli stabilized and you have very simple classical solutions. You don't need perturbative corrections, you don't need non-perturbative corrections. Now, Mark Hertzberg et al., they checked whether these simple models actually give rise to de Sitter vacua. And they studied a couple of models and they scanned their parameter space and they found no, that doesn't really seem to work. So then they sat down and actually wrote down a kind of no-go theorem that Kumrun mentioned already. So they just looked at two particular simple moduli, essentially the inflaton, the dilaton and the overall volume. And they wrote down how all these fluxes scale with the overall volume and with the dilaton. And what you see here already is kind of this Maldacena-Nunez no-go theorem. If you don't include O-planes, all of these terms are positive because all of these A's are positive. And then you have just terms that go like 1 over rho or 1 over tau to some power, and you will find there is no de Sitter solution. However, if you add O-planes, then you have a negative term. In principle, in these setups, you can circumvent Maldacena-Nunez. So there is no reason a priori that they don't give de Sitter. But what these people showed is that if you act with this kind of operator, you get 9 times V back, no matter what all the details are here of these other moduli-dependent values. And this forbids in the simple class actually de Sitter. So de Sitter would require that V is positive, so 9V has to be positive. However, on the other side, you see first derivatives. So the first derivatives can't vanish. So that means you can't get grad V equals 0. And this was then generalized by many people. And there's a lot of work, and I didn't cite all of them, but it was summarized in a paper I wrote with Marco Zagerman, and there we gave this kind of table where we studied in which cases no-go theorems arise and in which case no-go theorems arise. So in particular, you have a no-go for certain OQ planes and FP fluxes, where these are the lowest values. And what you see here is that generically you get something of order 1. It's slightly larger, so here's 1/3 or 12/7 as the absolute lower bound. But generically it's some values of order 1. So in that sense, no matter whether Kumrun's conjecture is correct or not, it seems in many string theory cases you find, which also essentially was shown in Kumrun's paper as support of the conjecture, you find these kind of exponentials with some order 1 coefficients. So it might be very interesting to study these models that have some kind of epsilon is 1/2 c squared of order 1. However, in this case, one also finds there are many examples with no-go in this particular rho tau plane. But this no-go doesn't necessarily mean that there is a go. So in particular, you would need some F4 planes, O4 planes with F0 flux, but the F0 flux is odd under this orientifold projection, so it usually is projected out. So those cases kind of get killed. Similar F1 flux is usually odd under the O3 plane projection, and in some cases you can't stabilize all moduli classically, then you would need to look at more complicated setups. So No-go doesn't necessarily mean go, but in some cases, like this 06 with F0 plane or 05 with F1 plane, we actually looked for concrete examples. And I should say before I forget, so these no-goes have been refined and extended in the last few years by David Andriot, I think, who's speaking tomorrow. Yeah, so he might probably also say much more about this. What I wanted to say is that in 2008, so with Dieter Lust, with Danielson, Gary Shiro, Thomas van Riet, and many other people, we actually looked at concrete models and saw whether they can give rise to de Sitter vacua. And the outcome of this was that we didn't find a single de Sitter vacuum, but we found in certain models de Sitter critical points. They always had at least one kind of tachyonic direction, and there was a no-go theorem which partially explains these, derived by Daniel Junghans and Marco Zagerman in 2016. So there was a reason why all of these models have essentially this tachyon. And now I wanted to switch a little bit gears and come back to this tachyonic de Sitter critical points in a few slides. Sorry, I think before I do that, I point out some shortcomings. So as Dieter was emphasizing, you have to be now always very careful. You have to spell out all the assumptions that go into the no-go theorems, and similar, you have to spell out all the assumptions that go into your counterexamples or potential counterexamples. So these constructions, I said, they're classically, they are somewhat simpler, but there are also some kind of subtleties that I don't want to sweep under the rug. So one thing is, they live to 10D. We can solve the 10D equations of motion. However, we can only do that in an integrated fashion once O-planes intersect. This is a general shortcoming. Nobody can solve equations for two intersecting sources. So solving the integrated equations, we can show there's no obstruction, but we cannot explicitly calculate the localized solution. We so far never included some blow-up modes from orbifolding. There's one paper where people actually do that, so I think one can probably include that. It's just some extra work. Once you do more general compactifications which go beyond Calabi-Yau, so these group spaces, I should have said that they have curvature. The question is, what are these moduli? So that is a little bit trickier to understand and to work out, but there's some kind of consistent truncation one can do to a certain subset of fields. That then gives the corresponding solution. Some people don't like the mass parameter in type 2a, but there are also T-dual solutions in type 2b, which don't have a mass parameter, which only have F1 flux, which I think nobody can object to. And I mean, flux quantization is not so much a subtlety, but it's something that initially we didn't worry too much about because we found these solutions. We said, fine, here are de Sitter maxima saddle points. They are not phenomenologically interesting because they have a large eta value. So we didn't really worry about imposing flux quantizations and all these issues. If you do that in the simplest example, which we only did here for one single case, then you find all of these solutions are actually at strong coupling and small volume. So in the very simplest example, this leads to issues. So you can't get large volume and parametric control of corrections. And now let me switch gears and tell you for a second about something else. So if you look at Joe Polchinski's string theory book, page 140, you read there that we conclude by analogy that D-branes spontaneously break half of the supersymmetry. So in flat space, they break the 32 spacetime supersymmetries to 16. So D-branes don't break supersymmetry explicitly, they just break it spontaneously. The same is true for anti-D-branes. So this has been known for a long time, but in the last 3-4 years, this had led to some much better understanding of anti-branes, which we have heard plays a crucial role in KKLT and LVS as one particular concrete example of uplifting anti-de Sitter vacua to de Sitter. And there is now a very nice way how one can describe that within supergravity, and many people here worked on it. I think Angel Uranga, Fernando Quevedo worked on it, Marjorie, Susha, Yvonne, So many people worked on understanding that better and rewriting this anti-D3 brane action in terms of what is called a nilpotent chiral multiplet. So you have a regular chiral multiplet in n equals 1 for the supergravity, and you impose a condition that it squares to 0. These particular kind of supergravity theories, they are called de Sitter supergravities, since in the simplest case, if you just include one chiral nilpotent multiplet, you can already get de Sitter, which is not possible in standard for the supergravity. So de Sitter is somehow easier to get in these for the de Sitter supergravity theories. So what I was working on with Renata this summer was trying to generalize this beyond anti-D3 branes to study any kind of anti-D brane in any kind of type 2 flux compactification. So Mariana Grania, she wrote this beautiful review about SU3 structure compactifications of type 2 string theory with orientifold projections, and then you get some 4D n equals 1 theory, and all of these reductions are worked out. I think in the type 2 on Calabiao, it was first done by Grimm and Lewis, and then many other people worked on more general SU3 structure cases, and people know what the low energy effective theory in 4D is in terms of a Kähler potential and the superpotential. So this has been known and this has been studied, and you can package it in many different ways, all the Kähler moduli and the complex structure moduli and the dilaton and so on. And what we now looked at is what happens if you add anti-D branes. So this anti-D branes, similar to D branes, they have to wrap some kind of calibrated cycle. In this paper by Dieter Lüst and Fernando Marchesano, Luca Matucci, Dimitrios Simpis, they called this pseudo-calibrated anti-D branes. These pseudo-calibrated anti-D branes, they said they break all supersymmetry. We would say they break all supersymmetry spontaneously, and the supersymmetry is still nonlinearly realized. So you have some nonlinearly realized supersymmetry, and essentially in these setups you get one new term to the action, essentially for each anti-D brane. So one simple way is this argument by Maldacena, where you say, I leave all the background fluxes constant, I just add a brane anti-brane. The Chern-Simons term cancels and the dBi term adds up. So you get 2 times the dBi action, which I forgot the 2 here. There's 2 times this, essentially. But this is also true if you just modify the fluxes and add an anti-D brane. So you don't need to add brane and anti-brane, which might be unstable. But you can just add anti-D branes and you get 2 times this term. And what we showed in this paper for all P branes, one can include that in terms of the 4D n equals 1 supergravity that was known before. One just needs to couple it to a particular nilpotent superfield. And so this I rewrote here. We worked out kind of the particular expressions. So you take the Kähler potential that you had before, the old one, and you add a term KSS bar, which depends on all the old fields, and multiply it by SS bar, and you add one term to the superpotential, where mu is essentially this mu squared is the square root of the tension. And this KSS, we worked explicitly out for all anti-D branes, so for P equals 3, 5, 6, 7, 9. And this KSS depends essentially on the modulus that parameterizes the cycle wrapped by the anti-brane. And the new term can then be rewritten very nicely in terms of e to the k nu, derivative of this new superpotential, the inverse of this, times this. So these derivatives give you just simply the mu to the fourth, which is the anti-D brane tension here. And the KSS is essentially this part where you use the calibration condition from whatever, Dieter and Ralph's review article. And then you just rewrite it in terms of the appropriate moduli for this particular theory. So that is very nice. And the simplest example of this is the anti-D3 brane uplift in KKLT and LVS, where you can write this simply by using T plus T bar to some power n, where n is 0, n is minus 1, warped for the anti-D brane, and mu is just the anti-D brane tension. And if you want to include complex structure moduli and axiodilaton, and that was worked out by Yvonne and Susha, you get some extra dependence here. So I just wrote it down for fixed axiodilaton and complex structure. we generalize that to other branes. And particular interest, now going back to what I was talking about before, is the anti-D brane, the anti-D6 brane. If you add anti-D6 branes, then you get one new term to your scalar potential, and you can write it in terms of K and W. So you get one new term to the scalar potential, and every new term affects, of course, your possibility of getting de Sitter vacuum, of having stability, of no having de Sitter vacuum. And this new term in particular takes this form, so there's some volume, and then you have a certain number of D6 branes wrapped around the kth cycle, and the ZK, they parameterize the complex structure moduli. So they're H2,1 complex structure moduli, and they are wrapped by some anti-branes. And then you can add this new term to the previous construction, and you can ask what happens to the tachyon. And in the very simplest case, with one modulus, which I call here MZ, we had initially a tachyon. So we had something like this. We had a de Sitter solution with a tachyon. And then you can check this new term, which are colored black here. It actually goes like 1 over MZ cubed. So it looks like this. So if you can appropriately tune this number of anti-D6 branes, then you can actually find de Sitter vacuum. So similar to the anti-D3 brane uplift, the anti-D3 brane uplift takes you from ADS to de Sitter. Here you're already in de Sitter, but you have a tachyon. So here, this kind of extra uplift new term, it can lead to stable de Sitter vacuum in the setup if you appropriately tune the number of branes here. So intuitively, this seems to work, and there are also deeper reasons why this might actually work. So this tachyon is essentially related to the S-Goldstino field, which in supergravity is usually a problematic field because you can't give it an arbitrarily large mass. So it's usually very light, and it's at risk of becoming tachyonic. However, once you add this anti-D brane, essentially the anti-D brane breaks SUSY, and it breaks SUSY in such a way that there is no S-Goldstino. So supersymmetry is here non-linearly realized. It's completely broken. It's a slightly different situation, and there is no S-Goldstino field. So there is no field that can become tachyonic. So in that sense, this kind of cures it in a very nice way. And we also looked at this simplest example that we discussed before. So this was this S3 times S3 mod Z2 times Z2, where we did some isotropic solution, and this always had a tachyon. And this tachyon is along these directions along which one can wrap actually an anti-D6 brane. And then we added to this example now certain anti-D branes wrapped around the appropriate directions. And what one finds is the tachyonic direction actually disappears. So the solution value shifts slightly, and the obstinate tachyon is gone. The issue which I mentioned before is that essentially this solution here was at small volume and strong coupling. And now this has slightly shifted, and in principle you have some kind of new parameters, which are the numbers of anti-D branes. But I suspect it might not be enough to get you away from small volume or large coupling. So I tried to scan that yesterday in the airplane. I didn't quite finish, but it seems all solutions might still be at small volume and large coupling. So I talked to two people who have worked on this. They're both not here. But one said, oh, this is obvious. This is the simplest example. You have only one O-plane. You can only choose your fluxes between 1 and 2. There's no way to tune that and get a volume that is much different from 1 or 2, and similar to get a coupling that is much different from 1 or 2. And some other person said, oh, this is very clearly a sign there are no de Sitter vacua. These are always at strong coupling in these models. This is a tiny island of moduli space, and if you try to somehow get it on your flux quantization, this is so tiny that you don't have the freedom to really go to large volume or small coupling. I don't know what is true, but at least here one has some kind of way of making progress by studying more complicated examples. So we have already some more complicated models with tachyons. One just needs to add these anti-D branes and see whether one can also uplift the other examples. and whether that helps somehow to go to large volume, or whether there's some deeper reason why these are always at small volume and large coupling. Okay, so this kind of brings me to my conclusion. So it's a very exciting time. Kumrun made a very interesting conjecture and spoiled my whole summer vacation, but it was it was a very exciting time. And yeah, I mean, the implications for cosmology are, of course, tremendous, as should be stressed and has been stressed many times already. Yeah. So what I have been talking about was some kind of recent progress in understanding somewhat simple classical solutions. We can understand them in 10D and 4D. There's some consistent truncation, so we can solve the 10D equations, 4D equations. Hopefully, in a few months or so, we might be able to understand these a little bit better. So, yeah, if we go beyond this very simplest example where things don't seem to work, and maybe we see that there's a general reason why it doesn't work, or maybe we actually find some that have large volume and weaker coupling. I don't know. But this is something we're currently working on. And hopefully soon we will make some progress. So thank you very much and stay tuned.
Are there any questions? Yes.
Yeah, this is very naive, but so you emphasized that in 10 dimensions the only effect is to put a factor of 2. The only effect of adding an anti-D6 is to add a factor of 2. But so why don't you just add a factor of 2 in the potential in 4D? And how come you get an extra term?
Sorry, you get exactly what you had before, plus 2 times the dBi action from the anti-brane. But so you get a completely new term. Before, you had an O-plane which has similar terms, or you had d-branes which have similar terms, but all of these were already incorporated in your previous scalar potential. And they get combined with the fluxes in a very particular way to form a complete square. This term does not. So everything we had before fits in terms of an F-term potential, in terms of K and W, in terms of usual n=1 supergravity. And that has a Goldstino in particular, which is a scalar partner of the Goldstone, and that is at risk of becoming tachyonic. This new term does not fit into that framework, and it doesn't have a Goldstino. So in that sense, there is a completely new term that doesn't combine with the rest and doesn't play as well, or doesn't play as before. Yeah.
Just another quick naive question. This anti-D6 cannot cancel with the other D6, and maybe this would translate it into another type of instability?
Yes, exactly. Yeah, it's a very good question, so I should have said that more. If we only put O-planes on the cycle that is wrapped by the anti-d-branes, then they couldn't annihilate, but there generically will be some flux. So then this is kind of what Thomas mentioned, maybe I should have said that more. There is a possibility, because the flux is essentially like some kind of smeared D6 brane, that there could be some instability. So I have the expectation that for a single anti-D6 brane, there might be no instability, but maybe Thomas would disagree. I don't know. I mean, certainly if you put many anti-d-branes, then there is a worry that they could annihilate against the flux. And obviously, if you put a d-brane and an anti-d-brane next to each other, they might immediately. But that you can avoid, at least in the simplest example. I checked that. Yeah.
Okay. One more question there.
Yeah. Well, what you explained, I see lots of relations or similarities with the proposal in KKLT. So, well, after all, when you put the nilpotent Goldstino and you add a new term, which is based in the dimensional reduction of the dBi action, by assumption, you're neglecting all back reaction on the internal geometry.
No, because here, I mean,
it's the same story our paper was about. It was, when you're putting the dBi action, it's you just take the backgrounds as something given. And,
no, I think it's very different, because here I have all these classical terms and I just add them up, including this new term, and I minimize the full action. So it's not I'm minimizing the action, then I somehow add a new term and forget the back reaction. I add to my actions a new term, and I minimize the full action. So I minimize the entire action, including the old terms, the new terms, and everything in there. So the back reaction is completely included here, I think. So there's no, yeah.
Well, yeah, that's what you're doing after all, putting the first potential plus the second potential.
And then I minimize the whole thing.
Yeah, I agree there. I would say, it's an open debate at the moment, but same as with the anti-D3 branes, we found Alamaldaten and Núñez say that you couldn't have just A plus B. Well, I think it could well be, and I would expect that there's some reaction on internal geometry.
But I take this into account. I think this is in that sense very different from the anti-D3 brane where you have the Gaugino condensate, which you might or might not be able to describe in 10D via the D7 brane, and then you try to couple it. And here, I don't have any such issues. I really take the back reaction of this on all the closed string moduli into account. The only thing is that it's kind of in an overall smeared limit, which is not the fully localized solution. But I think it is somewhat different from the Gaugino condensation, and I think Thomas agrees for the anti-D brane there.
We can discuss about it.
Yeah, I think there's now an excellent opportunity to continue this debate. So, is there one more question, perhaps, or? Yeah. Okay, that's the last one.
I was just wondering, what about the D-brane moduli? How are they accounted in all of this?
Yeah, because so cancelled they are not, but so that essentially one can include them, which we haven't done yet because this was our first step. We kind of didn't include the open D-brane moduli. There might be a possibility, I think, similar to anti-D3 brane, that you put them on an O6 and then the scalars would be projected out. But one can also include them as a constraint multiplets and add them to the 4D action or to the full action. But I'm not too worried about them because I wouldn't know how they could run away. I mean, essentially they parameterize the position of the anti-D6.
The thing I'm worried about is, I think in type 2A, I mean, an anti-D6 is just the D6 wrapped the wrong way round.
Yes, exactly.
So let me wrap it the right way round.
Yeah.
And then I start to miscalibrate it.
Yes.
If I miscalibrate it a little bit, you can understand it as a D term.
Yes.
If you miscalibrate it by 90 degrees, it's an anti-brane.
Yes, exactly.
So let me miscalibrate it a little bit.
Yeah.
Then it's essentially doing D term uplifting.
Yeah.
And this is an idea that Fernando Quevedo and people proposed a long time ago. And this idea, at some point, people found that there's a problem with it, which is that the brane moduli will just cancel the Phi-Dilopoulos term that you're inducing, but it's miscalibration. So yes. I don't see why this doesn't happen in this scenario, because it's just a continuous, they're continuously connected.
I mean, I would say I could put it on top of an O6 plane, and then I don't see a way how these open string moduli could survive. They should get projected out just because there's some Z2 projection, so they have to be set to 0. So in that particular case, I certainly can see a problem. In other cases, we haven't worked it out yet.
So maybe we should stop this discussion here, because we can easily continue afterwards. So let's thank Timm again for this talk.
Okay, thanks to everyone. Now the reception is coming. In about 10 minutes, we will have it on the 5th floor, on the rooftop of the building, okay? So in 10 minutes or so, get to the elevators, go to the 5th floor, and then you will see the light. And